Okay, let's see the solution of test 25. The question is, a current I is uniformly passing through a long cylindrical conductor with a radius r. Find the magnetic field at the distance r, which the small r that less than the big R from the axis of the cylinder. Okay. It means that we want to calculate the magnetic field around this position that is at a distance r from the center of the cylinder. And as we have discussed before, that this system has a symmetry. This is a cylindrical symmetry, and when we have the symmetry, we can use the Ampere's law to calculate the magnetic field. This is the Ampere's law. Okay, and to calculate the magnetic field at this point, we will create a closed loop which which share the same axis with the cylindrical conductor and has a radius r, which is the distance from the axis of the cylinder that we want to calculate the magnetic field. We know that the current I is a uniform current. When we say that the current is uniform, it means that the charge that move in this cylinder, the area density, which means the charge per unit area that pass to the cross sectional area of this cylinder, is a constant. It means that the charge per unit area are equal everywhere on the cross-sectional area of the cylinder. So we can calculate the amount of charge that pass to the area that has this closed loop as a boundary, and from that we can apply the Ampere's law to calculate the magnetic field. Okay. First, to do that, we look at the symmetry. The first symmetry is that we know that B will parallel to ds. Here ds is a displacement vector. The displacement vector that lie along the closed path here. Okay, and it follow the right hand rule. If you point your thumb in the direction of the current and curl your forefinger, that is the direction of ds around this closed loop. Okay, so B, when we know that B is parallel to ds, it means that B dot ds is equal to the product of the magnitude of the of these two vectors, which is B ds. Okay, so we know the form of B ds here, and also from symmetry we know that B is constant because the current is uniform through this cylinder. So there is no reason to expect that the magnetic field here, and here will have the different magnitude, because it will see the same current that pass through the loop. Okay, so we can assume that B is a constant, and from these two conditions, when we calculate this integral, we have B dot ds is B ds, and B is a constant, so we can take B out of the integral, and we have the integral ds left, and the integral ds is nothing more than the circumference, the length of the circumference of this loop, which is 2 pi r. Okay, so we have the left hand side of the Ampere's law, and the right hand side is mu0 or mu naught I prime. Here I prime is the current that pass through this loop, pass through the cross-sectional area that inside this loop, and we call it I prime. And since we know that the current is uniform, it means that we can calculate I prime from the ratio of the area in this loop to the total area of the cylinder, which is pi small r square over pi big R square times the total current I. This is a condition. This follow the condition of the uniform current. Okay. Now we know the I prime, and here you can see that the pi cancel. Okay. So this become small r square over big R square times I. So we can substitute this I into this I prime, this expression of I prime here, and we get B. In fact, B times 2 pi r is equal to mu 0 r square small r square over big R square times I, and if we rearrange, we have this B is equal to mu 0 I prime over 2 pi r, which is equal to mu 0 small r square I over 2 pi small r times big R square. And you can see that this small r cancels the square here, so we get the answer, that is mu 0 I r over 2 pi big R square, and the answer is number 2.